will be just very trivial. So almost all mechanical systems are evolving on curved spaces. Any question about that? Okay, so this branch of geometric mechanics is to study these systems, and geometric control, which 276 is to control these systems. Yes, please.
In the previous cases, all the surfaces were in the same plane, but here you actually changed the plane.
Hard dimensions, that's fine. I can go 10 dimensions, but they are curved. It's not changing the planes, it's adding more dimensions. So the first one was just one dimensional. Okay? So it's one dimensional embedded, it's placed in a two-dimensional space. This guy is two-dimensional and embedded in three-dimensional space. The same here, it's two-dimensional embedded in three-dimensional space. Okay? You can add more and more. I can have S1 cross S1 cross S2. It depends on your system. If your system are characterized, here we were talking about maybe single mass or double mass. But in general, remember Lagrangian mechanics. I'm talking about the configuration space. The configuration space of a whole mechanical system. Configuration space of a mechanical system is not concerned with a single mass. It is concerned with the whole system, the entire system, right? Your Q1, Q2, Q3, Q4. Maybe the first Q1 and Q2 belong to one mass, the second Q3 and Q4 belong to another mass, and so and so, right? But if you view them all holistically, this is the main difference between Lagrangian mechanics and Newtonian mechanics, where you have to isolate masses. So these all Q's, they form some space, hard dimension. What I'm claiming is that this space is typically curved space. Was a question here? No? Yes?
So the configuration space is just only possible locations?
Yeah, all the possible positions.
Not the actual trajectory?
The actual trajectory will lie on that space, right? Depending on your initial conditions and forcing and all that, right? Yeah, so your trajectory will be in that space. So for this two-link manipulator, if I start here, I will do something very funky moving along the torus. So now, well, we have our very basic space. It's the very first thing that you identify in your mechanics problem, is to identify your Q's, little Q's, degrees of freedom, which they form a configuration space. This is the very first step. We realize that this leads to a curved space. So now we need to do or perform calculus, differentiation or integration, both. Need to do calculus on curvy spaces. Do you need to do that? Then it's actually the branch that does it for you is called differential geometry in math. If you want to do calculus on curvy space, if you have a function that is defined on the real line, we know how to differentiate it very well. Partial x, partial y, or whatever. If you have a function that is defined on a sphere, then, well, we actually don't know how to do that yet. Okay? You need differential geometry to do it in a mathematically rigorous way. So differential geometry is the mathematical branch that allows you to perform a calculus on curvy spaces. It is a language more than anything else. It is a language. Okay? It is a language. We learn a language. Okay? Like here is maybe one of this language that we call the sphere S1. We call the unit circle S1. We call the sphere S2 and so on and so on. This is part of the language. And this language actually leads to very nice results. Okay? So let's know a little bit about this language. The first word in the language, guess what? Well, has to be my space itself. What are you going to call it? You're going to call it configuration space? Well, this is not only for mechanics. If it's mechanics, yes, it would be called configuration space. But we're dealing with anything else. It's a calculus, right? You can apply it to mechanics, you can apply it to anything else. So the first word actually has to do with this curved space. How are you going to define your curved space? It's called the manifold. Okay? So let's define what is the word manifold is. A manifold is a space, and we have to pay attention here. That is, look at this. Every word has a meaning. A space that is everywhere, everywhere. Locally, diffeomorphic, I'm going to talk about that in a minute, to Rn, Euclidean space, flat space. Let's understand this. We're defining our curved space. We're giving it a very precise mathematical definition. Well, any curved space now on, we're going to call it a manifold. Okay? So this is actually called the configuration manifold. You will find it in books and papers as configuration manifold. Okay, what do we mean by manifold? How mathematicians define manifold? They say it's a space. Well, please just bear with me here for a minute. Here is a space. Your space. Everywhere, meaning that the following has to be satisfied at everywhere, at every point in the manifold. Okay? In particular, here is one point. Tell me, please, what has to be satisfied at this point? Okay, the following has to be satisfied at every point. What's the following? Locally, around the point, so here is the point. Locally, just take some neighborhood around the point, call it U, neighborhood, okay? Okay, what does this neighborhood has to satisfy? It has to be diffeomorphic to Rn. Just easy. What do we mean by diffeomorphic? Diffeomorphism. Diffeomorphic simply means smooth one-to-one relation with a smooth inverse. This is diffeomorphic. So means that if you have two spaces, remember that when we define the function, we said it's a map between two spaces. These two spaces can be anything. Anything, days and fruits. Remember that example? We really mean that. We really mean this generality. Any two spaces, days and fruits. They have a map between them. This map maps any element here to an element there. Well, let's say that the map has to be smooth. There is no discontinuities, no jumps. You can differentiate it mathematically many times. And it has to be one-to-one. It maps every element to a single element here. This element has to be mapped to a different one. Cannot have two elements mapping to the same point. So x squared, the map x squared is not diffeomorphism because it maps negative 1 and 1 to the same point, right? So it has to be one-to-one. And if it's one-to-one invokes the definition of an inverse, well, we also requiring that this inverse is smooth. Okay? So this is basically the diffeomorphism. Whenever you have a map, x cubed, for example. So, but not at the origin, because it's not smooth at the origin. But anyway, so whenever you have a map that is one-to-one, smooth going, smooth back, we call it diffeomorphism. And think about it. If this is really the case, if every element here is corresponding to one and only one element there, and you can go from here to there very smoothly, you can go from here to there very smoothly, it's as if these two spaces are almost the same, right? Actually, mathematicians, when they are trying to say these two spaces look like each other, they say it in this words. Diffeomorphic to one another. Okay? So when mathematicians say this space is diffeomorphic to that space, they are trying to tell you that these two spaces look like each other. They are almost exactly the same because every element here corresponding to one there can go from here to there and vice versa. So, going back to the definition, it's a space. This is the black statement. Everywhere at every point, locally around the point, this neighborhood around the point is diffeomorphic to Rn. There is a relation, I'm going to call it phi, that map this red neighborhood to a flat space, Rn. Flat. Okay? Just flat space. Well, without going very deep, this can be explained in a much simpler way. The Earth is really curved globally, but locally around any point, here is a point, locally around the point, look around, it looks flat, right? At every point in the sphere, just sit in that point, look around, it's flat, so the sphere is a manifold, okay? So, any question about that so far? So again, a manifold is a space that locally looks like a flat space, okay?
What do you mean by a flight? So, what the
By-
flight situation?
By what? I'm sorry?
What is the flight means?
Flight?
Yeah. What does that mean?
Where flat?
I didn't say flat.
Flat,
Yeah.
I'm sorry, flat, like,
Yeah. So what's
It's not
the
curved.
situation can we call the flight?
what is what?
What is the situation we can call it the flight?
Okay, this is a very good question actually. I don't know how deep you want the answer to be, but I'll explain it in a minute. Okay, I'll explain it in a minute.